Hi everyone, this is just a quick intro video for 3.5. 3.5 is all about the physics application work, and I used to have, last quarter I made a little type up version of this, but I can't figure out where it is, so you're just going to get a quick handwritten version with some notes. So work is a physics application. I give you the disclaimer that I'm not a physics teacher. I'm a calculus teacher, so we're looking at the math, but it's a really nice one. It's kind of a culminating topic from the areas and volumes and then density problems we've been doing. So, big thing you need to know is the formula. Work is defined as force times distance, so it's really important to realize that this isn't just, oh, that was really hard work, or I'm going to work today. This isn't just the English word work. This is a very specific physics definition of what work is. So it's a force multiplied by a distance, and there's just one really picky bit to this. Direction is really important. So when we're looking at the distance, this has to be the distance traveled in the direction of the force. So if we're thinking about doing work against gravity, gravity is exerting its force down, and so we're having to exert a force up to oppose that. So the important thing would be for the distance to be up or down, so up in particular if we're doing work against gravity. So our force is going to be opposing gravity, and our distance needs to then be up. There's also some unit stuff in here. I don't need you to become crazy units expert, but they can be really helpful and you should know a couple of them. So let's see. If we know that making a product of force and distance gives us work, we're going to have first metric system distance. Oh, hold on, I'm in the wrong order here. So force would be newtons and distance would be meters. And newtons I can even break down a little for you to explain something that I'm going to talk about in a minute. Newtons are kilograms times meters per second squared. Kilograms. There we go. When we multiply force times distance, we get newtons times meters, which are otherwise known as joules. I'm not going to be offended if instead of writing newtons, you write kilograms times meters per second squared. If instead of writing newton meters, you write joules, or instead of writing joules, you write newton meters, I guess is more my point. I'm not that worried about it, but you do want a little familiarity with these units so that you know if what you're getting makes sense or not. We'll also see force represented by pounds, and distance as feet, and work will be foot-pounds. And we don't have an abbreviation for the foot-pounds, it's just that. So joules and foot-pounds are units of work, newtons and pounds are our units of force. So in a lot, not all, but a lot of our problems, the force is going to be the weight of an object. So you will see a little bit of variety there, but expect to do a whole lot of force is weight, and then distance is lifting something up. So notice that when we use pounds, that's already a weight and we're set. This can get a little confusing when we're metric because people will confuse weight with mass. Like if we're talking, I weigh so many pounds, and then they'll translate that into kilograms, but kilograms is not actually a weight. Kilograms is a mass. So if we want it to be a weight, we have to multiply it by an acceleration. So here, a little side note here. So this won't matter if you've got pounds, but it matters a little bit. Force is equal to mass times acceleration. Okay, so again, if you're given an object's mass instead of its weight in newtons, I guess is how you would say that. If you're given kilograms instead of newtons, you're going to have to get acceleration in the mix. And once again, since we very typically look at the weight of the object being the force and the distance being lifting it up, the acceleration, this is where gravity would come into play. So negative 9.8 meters per second squared. So what do I want to be clear about? I want to be clear about the fact that if you're given pounds, it's already a weight. If you're given kilograms, it's a mass. Make sure you multiply by 9.8. And we don't even, I'm going to erase the negative for now because yes, usually we would consider that headed down. But if we're talking about force, we don't need the minus sign. We're already lining up our distance going the right direction. So we've already got the signs worked out basically. So as kind of a byproduct of that, where this will come up, there's a couple of constants that are worth knowing. I think I give them in problems, but maybe not all of them. So just to have them all in one place for you. Constants that are good to know. Waterways, so I don't know what I would call it. I'm going to call the next one mass density, but this is like weight density. Water weighs 62.4 pounds per cubic foot. So you might need that for some of the problems. Again, I think it's included in some of them, and I've seen it rounded slightly differently. So something along those lines. Another one you might need if we're in metric is that the mass density of water is 1,000 kilograms per cubic meter. Again, so this is mass density. If you are looking for the force, if you're looking for newtons, so here, let me say it this way. To get force, you would have to take that 1,000 kilograms per cubic meter, and you would have to multiply it by 9.8 meters per second squared. And then you're still in a density, so you would also need to multiply by the, what are we looking for? The volume. So times the volume, which would be in cubic meters. So this might look very confusing having not done one. But again, my big point here is the 1,000 kilograms per cubic meter might be useful. If you're going to use it, you need to multiply by 9.8. The 62.4 pounds per cubic foot might be useful. You do not have to multiply it by gravity. Gravity is already incorporated into pounds. Okay, so I think that's all the background stuff that you need for this section. That should get you going. Hope it helps.